We saw in the previous video that we cannot just look at the training data to make decisions about the quality of the model, because we may always minimize the error on the training set just by overfitting the model. We saw that we need to evaluate the model on new and seen test data, and we saw the concept of the designated test dataset, a dataset that is sampled from the same population as the training set, but is not used in training the model whatsoever in any way at all. And so if we had a test set, what we saw is that the accuracy of the model on that test set is what we can use to estimate the accuracy of the model on new data. The problem is that we many times don't have a designated test dataset because obtaining data is expensive. We only have the training set. So what can we do in this situation? In this video, we're going to see a technique called cross-validation that is going to allow us to work around this limitation of not having enough data to estimate the performance of the model. And the idea is simply that we're going to refit the model multiple times under different subsamples of the training set. But the general principle is that we get the training set, we randomly partition it into different subsets. The first one is going to be the actual training set. It is the one we use to fit the model, to come up with the model coefficients. And the second set is what we call the validation set. It's the one we're going to use to evaluate the model with the measurement of accuracy that we want, and is going to allow us to estimate how the model performs on unseen data. So in a way, if you would, what we have is a validation set that acts as a test set. And what we do is refine this process many times, randomly partition into, use one set of the data to train the model, use the other set to validate the model, to test the model. We do that many different times, and so we have many different estimates of how well the model performs. Let's see an illustration. So we have the available data, everything we have. And what we do is split it in two. A large part of it is going to be the training set, and the other one is going to be the validation set. With the training set, we fit the model as usual, and then we check the accuracy with the validation set, which, as you can see, is not used in any way to train the model. It's only used to assess the goodness of fit. So we have the measurement of accuracy of the model given the validation set. This is estimating in itself the accuracy of the model on unseen data. So a few considerations first about what happens with cross-validation before we see more detail about it. If you think about it, the validation set is randomly sampled. We have to randomly split. And so our estimate of the error could vary too much across different data splits. Maybe for one data split, we have a very low error, but for another data split, we have a very high error. There is a random component to it. And actually here in the right, we have a picture of the error of a model by the complexity. And each of those lines represents a different split of the available data. And we see that we may have very different pictures depending on which specific random split we use. And so we have a new random component that is the split of the data. We have to account for this randomness or control for this randomness. If we also think about it, both the training and the validation sets should still be representative of the original population that the whole data set represents. And many times this is going to be tricky to ensure. So we could think about different ways of ensuring the sample is representative. For example, think about a stratified random sample. If we know that according to a categorical variable, we have different groups of data, and maybe some of those groups of data are highly underrepresented in the training set, then we have to ensure through stratified random sampling that those groups are still going to be equally represented in the training set and the validation set. So we have to think carefully about how we split the data. Also, we have to think that the training set is actually smaller than it could. If we have all these data sets and then we reduce it, splitting and only using this part for training, then we are not using as much data as we have to train the model. And so in principle, the model is expected to perform worse than if we used all the data to fit the model. So we have to account for this bias. The model is expected to perform worse because, well, we're using less data to fit it. And in the end, cross-validation is going to allow us to consider arbitrary definitions of the model accuracy. This is the power of it. We can use absolutely any definition of model accuracy based on new data, because that's precisely what we are emulating here. We are randomly splitting the development data into training and validation, and whatever we want to look at, whatever ad hoc measure of accuracy we want to use, we just use it based on the validation set. Whatever it's best for our needs, whatever is best for our problem. And so how do we control for this randomness in the splitting data? Well, there are many different ways. The one that is the most typical is called k-fold cross-validation. And the idea is very simple. What we do is randomly split the whole data set in k folds of the same size, in k different groups. And then for each of those groups, what we do is use all the other data to fit the model and use that data to validate the model. So for any fold I, what we do is use all the data except I to fit a model. So this is going to be the f sub I hat, an estimated model based on this data set, on this split of the data. And then we use only the fold I to validate the model. And so we do that many times, k times, and the cross-validation accuracy is then the mean accuracy over the k folds. So we just compute the accuracy k different times and average. Typical choices for k are 5 and 10 for different reasons. And you can think about the extreme case in which we do this precisely n times. So k equal n, equal the number of observations in the whole training data. And this is what we call leave one out cross-validation. So at any given time, we take away one observation, fit the model on all the other n-1 remaining observations, and validate the model on this one observation alone. We do that for all observations, and there we have the leave one out cross-validation accuracy. As you can imagine, this is very impractical with large data sets, so normally what we do is a k-fold cross-validation process. Let's see an example. So let's say we want to do 5-fold cross-validation, and this is all the available data we have. Step number 1, we split in 5 folds of equal size. And again, we have to be careful here, maintaining the representativeness of all the folds. So we have to be careful about how we split the data. What do we do? Well, let's take fold 5, for example. We said folds 1, 2, 3, and 4 as the training set. We fit the model. Let's call it f hat sub 5. And then we validate on the 5th fold alone. So we only validate on the 5th one. So this is the accuracy of this model based on this validation set. Then we do the same for fold 4. So folds 1, 2, 3, and 5 are the training set, and fold 4 alone is the validation set. So we compute a new model and the accuracy on a validation set. And then we do the same for folds 3, 2, and 1. In the end, we have over here 5 estimates of the accuracy of the model trained and validated on different partitions of the data. We compute the average of all those. Let's call that average through cross-validation. And this is what we use as an estimate of how well the model behaves on new and seen data. What do we achieve with this? Well, we reduce variation. So again, here on the left, we have the error of a model by its complexity. Each of those lines represents one fold in a 10-fold cross-validation process. So each of these represents the accuracy of the model given one partition. And what we see is that there is a very high variability. Just depending on which specific partition of the data you look at, you may have a high or a low error. What do? Well, we average those 10 lines into only one. And so here on the right, what we do is the 10-fold cross-validation process repeated many times so that you see that the variability decreases. Each of those lines represents the average across 10 folds. And so each of those lines would represent what you would observe in one iteration of your whole process. So you get a 10-fold cross-validation process, you compute all the folds, compute all the accuracies, and average. Then you would get a line as a result, only one line representing the average across all folds. And what we see here is that if we do that, then we don't have many variation or a lot of variation across different replications of the experiment. They are going to be very similar. And so this is what we achieve with k-fold cross-validation. Reduce the new randomness component that we included in the process by splitting the data in random. And so, for example, in this case, what we would do is, based on the data, if we want to minimize error, looks like pretty much anywhere with 2 or more in units of complexity will be enough, because beyond that, the model does not behave any better. So, with a little bit more detail, how do we select a model based on cross-validation? Let's look back at the examples we had in the previous video. So here in black, we have the true model. This is the model generating the data, so reality. And we had 3 different alternatives: a very simple model in orange, a okay model in blue, and an overfitted model in green. And then over here, we have the accuracy of the model on unseen data, so the true capability of the model. Now, we don't know what it looks like, right? The ideal model, based on this test error that we don't know about, would be somewhere around here. This is the model that minimizes the error. If we do cross-validation, we can similarly plot our estimate of the error as a function of complexity as we estimate through cross-validation. So it would be something like this green line over here. So it would be about choosing the model complexity that minimizes the accuracy in cross-validation. So it would be this point over here, more or less 8, 9 in terms of complexity. In the red example, we have the same thing, different alternatives. How do we choose one? Well, we could plot the line of cross-validation for each of them and just select the one that minimizes the error in cross-validation, which in this case, it would be a complexity of 5. So we select the model that maximizes the accuracy as we estimated through cross-validation. And if we think about it, there is a certain degree of random error in this cross-validation line because it depends on the splits on the data. Something that we can typically do is, all right, just plot as well the standard error of this line across faults. And then what we do is choose the model that is the simplest within one standard deviation of the optimal. So in this case, if the optimal is over here, this is the standard error, then it would be somewhere around there. This would be the one, because it's statistically indistinguishable from the optimal one. And so in this case, here's the optimal one. If we go to the standard error, what is the smallest one that is within one standard error? Over here. So that's what we would choose. So this is cross-validation. And again, we have to follow the same principles as with the test set. Any decision about what family of models we choose, about what predictors we use, about the complexity of the model, etc., has to be made before observing any validation data. So a typical wrong use of cross-validation would be taking a look at the whole dataset, look at the variables, their relationships, and based on that, make a decision in terms of what features we're going to use or we're not going to use, what class of models, etc., and then do cross-validation to estimate the test error. Well, we already made a decision based on a look at the whole dataset. It doesn't matter if afterwards we randomly split in 2, etc. We already made a decision based on the whole thing. So this estimate of the test error is going to be underestimated. The model is expected to perform worse than it shows through the cross-validation process. So just like we did with the test set, we should not make any decision about the model, not before, not after the process, based on a look at the test set. If we do that, then our estimate of the test error would be underestimated because it's based on a model that already takes advantage of a look at the whole data. And part of that data is what we are going to use in each of the data splits to validate the model. And therefore, we are, in a sense, already overfitting to the whole data.